Hello and welcome. You might be thinking, hey, what are we doing? We've done all of this advanced OpenGL stuff. Now we're back to the basics. What's going on here? Well, there's a little thing I call having fun, and that's what I'm doing today. I wanted to sit down and create a raycasting engine or a raycasting demo. It's a lot of fun to go back through the history of, computer graphics from the beginnings in the Wolfenstein days, and then up closer to present. Maybe even taking Wolfenstein and ray tracing it. Wouldn't that be insane? And I'm going to try do all of this in Python, which is even crazier. As you'll see, it works, but not well. What do we have? Well, if I Google ray tracing tutorial, there's one website which always comes up. And I remember years and years ago when I was first getting into computer graphics stuff, I would read this, and it's the classic. It's the one. So I'm going to take this tutorial, lowdev.org, and kind of adapt it to Python OpenGL. Just so we can see the basic idea of raycasting is we have a top-down, if we take a top-down view of the world, we have a player and we cast a bunch of rays from the player, actually one per pixel scan line, and however far it takes the line to hit an object is the distance of the object from the player. I wonder if we have any more. Anyway, something like this, right? So we run across from left to right and we scan and we hit objects and draw them. Okay, so that's basically what we're going to be doing. So let's just open this up. And this will be kind of running, it's like a little side chapter to the OpenGL stuff. So we'll go new folder, and what we'll do is make a flat raycaster. I'm also going to be, what are you doing there? I'm also going to be demonstrating some slightly different design patterns, or maybe the same design pattern. All right, so let's start with the imports. This should be pretty standard. So we import Pygame, OpenGL, NumPy, all this stuff that we've been using in the tutorials before. And then let's go straight to the shaders. So we'll go new folder, call that shaders, new file. Okay. So because I'm explaining, like the concept as opposed to the details, we've done this before in my other videos, there will be a lot of copy and paste today. That's also to keep the video under 5 hours. You don't want to just see me type. So what are we doing? All we're really taking in is a model transformation, because what is a raycaster? Well, when we draw walls, we draw a series of horizontal lines. So our engine is just going to have 2 points which define vertical lines, 2 points which define a vertical line, and we'll be scaling that and drawing it at different positions. All we need there is a model matrix. Let's go ahead and create our vertex shader. Fragment, I mean. Okay, and we'll copy paste some code in here as well. By the way, I'm also making this video, I don't know if this is necessarily the way to do it, but I'm also making this video because I couldn't really see any like modern OpenGL examples of raycasting. Probably with good reason, right? Okay, so what are we doing? Well, now we're also taking in a color as a uniform. If our engine just has a vertical line, then we can't really store color in the vertex data. And why would we want to? So instead we'll pass that in dynamically as a uniform, and all we're doing is just passing that out as the final color. So that's why we call this flat, because there's no colors, so to speak. Okay, so let's go ahead and get into the actual stuff. So I'm going to be using a model view control pattern. Okay, now for the model, we're going to have a player, and we're also going to have a class called GameBoard. Now what the GameBoard will do is store basically all of the objects in the scene which need to be drawn. Then for our view, we'll have an engine class, and it's the job of the engine class to draw, or it takes in a pointer to a scene and it draws all the objects in the scene. And then finally, in our control, we have an app. And what the app does is it takes, so it has, basically handles to everything. It takes input from the player, like, mouse buttons, keyboard and stuff, and it updates or tells the GameBoard to update itself. And it also tells the engine to draw the scene every frame. The way we start this is we go my app, and that will get things started. So let's have a look at the player first. Yeah, why not? Okay. So when we start to work on bigger projects, this is a tiny project, but when we start to work on bigger projects, it's really important to document things correctly. This might be a little bit over documented, it's fine. So if we use these triple strings, that opens up a multi-line comment, and this is what's called a doc string. Here's another example. Let me paste this in. So when we initialize the player, we call this init function, and we just have a description of the function here, as well as telling what the parameters are. And we can also specify, like if we return something, then we could say, return something. Returns a handle to the player, returns a pointer to the player, something like that. Okay, so this is really important because when we have this in a separate module and we import it and we forget what it is, so let's say we go to the app and we go we want to say something like so when we type the definition, we get a pop-up with the doc string which we wrote before, which is really useful because if this is in another module or a module inside a module, then instead of bringing up a bunch of different files, we can see that documentation straight away. So that's really important. Okay, so I'm happy with the player. That's all we need to do there because the player is basically going to be controlled by the GameBoard. So let's have a look at the GameBoard class. So again, I'll just be, pasting this in. The GameBoard description is it holds the pointers to all objects in the scene. Then we want to initialize it. Okay, so again, let's put a description here. So for now, we're going to be hard coding this. If you want to take this engine and extend it, you are more than welcome to, in which case a good idea would be to load this in from a file. So let's define the map. There's a bunch of different ways we can define the data for the map. I'm going to use the tried and true method of making a big list. So what we have here is we have a list of lists. 0 represents a blank space, and any other number represents a type of block or a type of wall. Okay, I think that's looking okay. Okay, now we'll define the player. So I'm declaring the player at 7.5, 6.5. So we count across. We have 0, 1, 2, 3, 4, 5, 6, 7, and then somewhere within 7 because we're 7.5, and then 6.5. So 0, 1, 2, 3, 4, 5, 6. So in here. So if we look at this, these zeros are like a hollow space. The player is going to be in here somewhere. Okay. Cool, cool, cool. So then what else do we need to do? Well, we'll need to move the player. So I'll just grab this. So what we're saying is we have the player object and we want to move it forward at a given speed. So first thing we'll need to do is we'll need to calculate the increment in position. So if we look at the, so we know what speed the player is moving at, we know which direction the player is moving. That's fine. So we take that speed, multiply it by cosine of the direction, but just remember the direction is being stored in degrees just to make it a little more readable, so we will have to convert that. Cool, and then we'll pretty much do the same thing with y to get the increment in the y dimension. Just bearing in mind that Pygame has a weird convention where negative is upwards and positive is downwards, which is the opposite of the sign convention. So to correct for that, we just multiply by -1. It's not a big deal. Okay, so what do we need to do now? Well, we could try to move by dx and dy at the same time and see if we can move there. But the player might also be walking along walls and we want them to slide, in which case they might be able to move in the x direction but not the y direction. That's perfectly fine. So what we can do is, I'll type this one out. So we'll say just want to check a few things first. So if we take, we'll call this like the new x position will be our position plus that dx. Round that to an integer because we're looking inside that array, which is all indexed by whole numbers. So first thing we want is we want to be bigger than 0 and less than the maximum. So less than or equal to, what do we have? This should really be less than, shouldn't it? Because if we've got 24 units across, then that's 0 to 23, so we want to be less than. Okay. Maybe that's why I was throwing errors before. Okay, let me just clean this up a little bit. Right, so everything's kind of reversed a little bit. Let me write a little bit more and then this will make sense. So we have, so we're just checking that our new x position will keep us within bounds. And then we go if self.map quickly actually get rid of those brackets. Okay, cool. So this is a bit funky, right? We're accessing the map in kind of the reverse order. We're going Y first and then X. Well, remember that what we're looking at here is each of these is a row. So by convention, the first element that we access within this multi-dimensional array will actually be the row, which if we look here, those are going up and down. So that's vertical, that's the Y coordinate. And then once we get in there, the next element that we access is the column, which is the X from left to right. So that's why we do that kind of thing there. And then for instance, if we pick the first row from the map should always have at least one row, and get the length of that, that will be the horizontal length maximum of the map. Okay, so then we can go ahead and do that. So we say self player x increments by dx. Okay, now I'm going to go ahead and do the same thing for y. And what this is doing is it's kind of testing the X movement independently of the Y movement. So I'll just fix this up. That should be less than. Okay, think that's fine. Think that's good. Okay, so we can move the player. The next thing we want to do is we want to be able to spin the player around. So we'll make a function called spin player. And we'll just kind of condense that. Not that much. What? That's not good. These should not be tabbed over that far. So I've accidentally put them within the initializer. Okay. Okay, so what are we doing? Well, we're saying, hey, we want to shift the player by this angle, which is either adding or subtracting the angle. So we just add that onto the player's direction. Then the only other thing to check is we might have a negative number or a number more than 360, in which case we just, keep it within the range 0 to 360. Nothing crazy there. So that is our, those are our model classes. Okay, I'm going to go onto the app. So again, just copy this in because it's important. Okay, so for the initialization, I'll just get rid of these lines here. What I was doing is during testing, I would run this once and then quit. Like run the render once and then quit, and then just print out a bunch of information, check the diagnostics, but that's all working now, so it's a good idea, but let's not do that right at the moment. Okay, so what have we got? We're just setting up a screen to be 320 by 240, initializing that with Python, Pygame. I'm going to have a clock as well. And we are going to create an engine class and a game board. Okay, so we'll go to the main loop. Sorry, I was just trying to grab that text. Okay, so this loop will run until the exit, basically. That's tracked by this variable here. This is a standard kind of pattern. Pygame event quit is just if a player hits the X button. So what do you want to do? I want to handle the keys, so I'll have a function for that. Then we want to render the whole scene, and then we also want to, just check the frame rate and things like that. After that's all done, then we call the quit function. Now we need to call the quit function because the engine will be allocating a little bit of memory behind the scenes, and we want to free that up. So let's go to handle keys first. Okay, so we get the state of all the keys, and these can be accessed just the same way as we would an array. It's a bunch of booleans indicating whether a key is currently pressed down or not. So if we hit W, that's moving forward, so we move with a positive speed. If we hit S, that's backwards, so we just go negative speed, and then we're just spinning the player around. So this is completely up to you. A fun extension, if you're following along, would be, hey, if you want to incorporate mouse movement as well and do strafing and things like that. Okay, so then we just have the quit function, which doesn't really do much. It just calls the quit function on the engine, pretty much. Okay, so let's get into the engine. And this is the, the meat and potatoes of it. Hope you're having fun. Hope you're enjoying my chilled out tutorial, chilled out version. Okay, so the engine is basically rendering. So what do we want to do? Well, let's just make this. So first of all, we want to initialize it. And we want to pass in a height of the screen. We store those variables as well as a clear color for clearing the screen. And we're going to call a create shader function, which we'll define soon, which will take some source code and compile it and everything. Okay, so now let's create the vertices for our vertical line. Remember, it's going to be the same vertical line which we draw repeatedly, so nothing too fancy here. So this is x, y, z. X of 0, because we by default want to be drawing directly in the center of the screen, and then we'll be translating that left or right depending on where we need to in the draw stage. And then, okay, so y of 0.5 is, positive a little bit. Y of negative 0.5 is negative a little bit. So just a kind of line segment going straight up and down. And z of 0 means we are directly at the screen level. No perspective correction needs to be done. Okay, so as you know, we can't just pass in a tuple or list or something. We need to convert that into a NumPy array. That's the data type which OpenGL likes. We've only got 2 vertices here, so we probably don't even need that, but that's fine. So now we'll just go through the standard procedure which we've done in a lot of the other videos of setting up vertex buffer and vertex array. So we create a vertex array object, we bind it, same with the VBO, and then we just pass in all of that data. So we're passing this into the VBO basically because that's bound. We get the number of bytes, we pass in the data, and we put that in static draw mode. That's fine, that's pretty standard. We only have one attribute which we need to enable, that's attribute 0, which is the position. So we go ahead and do that. Yep, so position has 3 components, x, y, z. They're float. They do not need to be normalized. They are already in normalized device coordinate form. Stride of 12 because we have 3 bytes. Sorry. 3 floating point numbers. Each floating point number is 4 bytes, so that's fine, and we're starting from position 0. There should really be nothing too crazy going on here. Okay. So the other thing I'm going to do is I'm going to define a variable called self_colors, which this will be used with the map. So the map had some numbers, you know, like 1 to 5. So I've declared 5 different red, green, blue combinations, just so that we can draw different wall types. And that's it. Okay, so now let's go on to create this shader. So actually exactly the same code as we had in other tutorials. We just take in some file paths and we, you know, open them up and read them and compile them. That's it. So again, if I go back a little bit, we call that function. Its return value is saved as self.shader. Okay, so the next one I'm going to write is, well, not yet, right? This is the big one. This is the biggest function here, so we can actually just leave that for now. We'll get back to that. Okay, so the last one is the destroy function. So remember, Python doesn't allocate memory. However, OpenGL does. Specifically, it allocates memory when we call, like, you know, create buffer, create vertex array object, all of that. So this is just freeing up that memory. Remember, if it's a really simple program, we probably don't have to do that, but it's a good practice to always do it, because if this becomes part of a larger program, well, then we might be starting the game and stopping the game repeatedly, and that will be allocating new memory every time. So yeah, there's that. Okay, so let's go and draw the scene. And this is the part which is probably the trickiest and probably the most math heavy. I'll do my best to explain it. I'm not great at explaining things on the spot, so I would absolutely recommend that you take your time with this. I mean, this is what I did. You know, I read this article, I did a bit of working out on paper myself as well, and I took like a good day or two just on this thing. Because when you have a problem in computer science, you know, don't be one of these people who just flits around and does a bunch of different little things. Like, do something, dedicate yourself to it, solve the problem, and be happy with that. What I'm trying to say is, there's a lot of reward in working the problems out for yourself. So I'm going to do my best to explain it, but you might have to do a bit of homework as well. Okay, so what we're doing is we're creating rays. The rays are going to start from the player and emanate outwards. So to start with, I'll create what I call view parameters, which is basically the position and direction of the ray. Position, it starts at the player's position. And then we have two kind of fundamental directions. We have the forwards direction and the direction to the right of the player. This is very similar to creating a view transformation matrix in OpenGL. So we take the player's direction and we get the sine and the cosine of that, and that will be the direction vector, which is a unit length of 1, pointing in the same direction as the player is viewing. Remember, we're adding that negative out the front because of Pygame's convention around sine. So we could be, there are two ways to proceed from here. They're both equally valid. One way is we want the vector which is pointing to the right of the player So if I just bring up this diagram here, so here is the player, the green dot. The forwards direction is this black line. The blue line is the right, well, really, this half is the right vector. And then what we're doing is we're taking a linear combination of the right vector and the forwards vector. We're interpolating between this point, and that produces a bunch of rays. So to get the vector which is to the right of the player, we could do exactly the same thing here, but subtract 90 from the direction. Or we could be a little trickier and we could say, okay, well, two ways to think about this. One way, the derivative of cos is negative sine. The derivative of sine is cos. So if we take this value here, what? Derivative of cos is negative sine. This is negative sine. Derivative of the forwards direction is cos. Another way to think about it is these two vectors, forwards y and right, like forwards and right, are orthogonal or perpendicular because their dot product is 0. If I go, first component times first component, I'll have fx times negative fy, and then second times second is fy times fx. Add that together, makes 0. Here it is. This is a vector which is always pointing right to the player's forwards direction. Okay, so now what do we need to do? Well, we need to create a ray, and we need to create a single ray for every pixel along the screen. So we'll go range self screen width. We probably don't even need to store screen height, but we will anyway. Okay, so the next thing we need to do is we need to track how far along are we. If we bring up this diagram here, at this point here, we want like x equal -1 basically, and then here we want x equals 1, and then here we want x equals 0. And we're going to add a proportion anywhere in between there, add a proportion of the right vector to the forwards vector. So this is summed up in what I'll call an interpolation coefficient, because we're interpolating from the left to the right. Okay, so now we want to create a direction for the ray, this particular ray. So let me just go through this, by the way. So what we have, ray index starts at 0. So we have 2 times 0 is 0. So this is all 0 minus 1. So that gives us an x of -1, the left-hand side of the screen. Then we set ray index to be equal or almost equal to screen width, in this case 320. So we have 320 over 320 is 1, times 2 is 2, and then 2 minus 1 is 1. So at the other end of the loop, we are 100% on the other side of the screen. We're at, x equals 1. Okay, anywhere in between that is kind of a proportion or a percentage. So we multiply by the right vector, add that on, and this is giving us the direction of each ray. The next thing we need is we need to know in which map space is the ray starting. Now we know its position, we know its direction, but we need to know which block are we starting from. Okay, now here comes the math bit. So we need to know something called, or the article calls it, delta distance. In other words, from each, go back to here. And by the way, massive credit to LowDev. This is an awesome tutorial. I'm horrible at explaining things. I would not be able to explain this as well as this tutorial. Okay, so we have two kind of things that we're interested in. The distance between the horizontal lines, that's the x distances, and the distance between the vertical lines, the y distances. Delta distance x is the progressive distance from one to another. Now remember, delta distance x, it's 1 unit across here, but there's also a step here. So if we use Pythagoras' theorem, it's the square root of the x component and the square root of the y component. The x component is stepping across by 1. The y component is stepping up by tan of theta, which is, y over x. Let me take the square of that. So we've got y times y over x times x. Then we have the fact that 1 plus tan theta is sec theta, or sec squared theta. Apply the square root of sec squared theta is just sec theta, which is 1 over cos theta. And cos theta is the, cos theta is the x component. So as we can see right down the bottom here, we get 1 over the x component for the delta distance. Then basically the same thing for y, just reversing the role of x and y. So we have 1 over the y component here. So that's what we're doing, basically, to get the delta distances. I'll just copy this in. And the same thing for the delta y distances. So what I'm doing here as well is I'm just checking if the result that if the x length of the ray is sufficiently close to 0, that means its absolute value is within this threshold, then just set the delta x distance to something really big. Otherwise, so this is just to make sure that we're not accidentally dividing by 0. NumPy catches a divide by 0, it's actually perfectly fine, but let's handle it ourselves as well. Okay, so we've got that. Now we need to orient the rays. So I'll start with the horizontal orientation. Just copy this in. So there are two horizontal orientations. We're either moving left or moving right. So hopefully this makes sense, just depending on what our ray direction is doing. We're either left or right. The interesting thing here, I guess, is this side distance x. So remember, side distance x is how far do we have to move from the player's position to get to the first line. I'm goofing this up, right? So these are actually vertical lines, and then side distance is the horizontal distance to the vertical line, if that makes sense. Whoops, wrong one. So what is that? Well, if we make a full 100% step across, then we'll go across by a distance of delta x. But otherwise, we are some proportion, right? So let's say the player's x position is 3.7. That is 70% across position 3. So it's, 70% times the distance, which is associated with one x step. Hopefully this is making sense. I do realize this is definitely tricky, and definitely tricky the first time you see it. And I don't know if YouTube's even the right place to learn this sort of stuff. Look, I'm not saying this is insanely tricky. It just takes time. Okay, so then we'll do the same thing for the y. Remember that in Pygame, -1 direction in the y is upwards. So that's just what we're doing there. Otherwise, it's pretty similar. Just double check my indentation. Yep, that is good. Okay, so now we will go ahead and actually trace the ray. Okay, so we've got our ray oriented and set up. We'll just like let it run, let it go. So we have to decide whether we are going to jump to the next horizontal or vertical line. And that decision is done. Yeah, looking at this code now, I'm double second guessing myself, but it is correct. So let me just jump back to the article. Okay, so we look at the red ray coming from the player, and as it steps, or maybe not this one here, as it steps across, it is either jumping to okay, this makes sense, either jumping horizontally to a vertical line or jumping vertical to a horizontal line. And in order to do that, it just makes a decision based on which is closer. So if it's closer to go to this line, then it jumps here. And it also keeps track of how far the ray has moved so far to get to that point. So that's what we're doing. That's what we're doing over here when we keep track of side distance. So that's saying how far have we moved to get to vertical lines so far. Okay, so again, try our best to follow along. I probably am not explaining this very clearly. So then what we need to do is note that we are tracking which sort of wall we've currently hit. So when this exits out of the loop because it's hit something, we will have a reference to the type of object that we hit, so we can test that. Now we need to use that to get the distance to the camera. Now what we could do is we could get the distance directly to the player, however, that produces some kind of fisheye effects. So what we'll do is we'll get the perpendicular distance, which is, again, I'm really relying on this article, but I mean, this is what it is. It's a weekend project. I'm just having fun. We're chilling. So, right, we trace along, we hit an object, and then we get the distance perpendicularly to the camera plane, which is given by this formula, which is actually, I didn't look into this. It's been through a few iterations of simplification. Okay, so now we get to the OpenGL stuff. So the interpolation coefficient that we defined up above went from -1, where are we? Went from -1 to 1. So that tracks how far our ray is to the left or right of the screen. And then the distance from the camera represents how high the ray should be. Like the further it is from the camera, the shorter it should be. So let's go ahead and set up our model transform. Okay, so we'll start with the identity and then we'll multiply in a bunch of these. So the first thing we'll do is we will translate this across. Now for the translation, it's just an X translation based on the interpolation coefficient, to the left or right of the screen, basically. And then for the height, we want to scale this. So we'll make a scale transform, and this probably doesn't matter. It probably should be about that, I guess. So scale factors, we are not scaling on the X, we are not scaling on the Z, we're just scaling the height, in other words, the Y coordinate, and that is the inverse of the distance. So the further away we are, we go to a distance of 1, a distance of 2, that's a half scale factor. Go to a distance of 4, that's a fourth, a quarter. Get closer, get a tenth, that's a scale factor of 10. So that's just setting up our perspective. Then we will go ahead and load that transform in. There, again, nothing that we haven't done before. Then we also want to select the color that we want to draw with. So we look at self.colors and we index that based on the actual thing that we hit. And I just realized I should be subtracting 1 because we don't want to draw when we've got a 0. We want to go from 0 to 4, basically. Okay, cool. So, oh, what's that? That's much better. Okay. Now we'll go through the job of drawing. So we will bind our vertex array and draw the line. So remember, this is just drawing a single line. It occurs within a loop, so that goes ahead and draws the whole screen. Okay, so and update the screen and everything. That should be fine. That should be good to go. So let's close that all up and give it a shot. Wow. That's not good. Okay. Yep. So that is line 83, probably in the move function. Yep, just this one here. But you guys saw that, right? Hey, I never see these things. Okay. Good, good, good. That is looking good. So there it is. Hey, that's awesome. We've got our ray tracer. We can walk along the walls and it's stable, at least as stable as something like this can be. It's also very slow. So before I was running this at 640 by 480 and it was running at about 17 frames per second, which is just insane. It is what it is. So yeah, there it is. What I'll be doing is in the next video in this series, we'll look at texture mapping, which hopefully shouldn't make it much slower because OpenGL, there usually isn't that much overhead to add texture sampling. All of the work is everything that's slowing us down is all of this Python work. So in Python, the CPU is incredibly expensive. If I wanted to speed this up, I would do it in C or C++. But that's not fun. Okay, cool. So that'll be it for now. See you in the next one. Bye.